All right. Hello, everybody, and welcome to our latest edition of Cosmos from the Couch. Thanks, everyone, for hanging with us for our slight 2-minute delay, but we got there on time. So my name is Dr. Maria Drought, and I am going to be talking to you this evening for the next hour or so about astronomical alchemy, the origin of the elements. So I'm guessing that if you're logging in for this talk, you're also not afraid of at least a little bit of chemistry. But I promise this is going to be an astronomy talk. And as you can see from the main background slide I'm showing you here, it's going to get pretty explosive by the end. So how tonight is going to work is I've got some awesome slides to walk you through on astronomical alchemy. I also have some people who are watching the YouTube chat for me, and so they are going to be passing questions on to me. So there is a slight delay in between when I speak and when it goes to YouTube and when it comes back to me. So they will be feeding these questions throughout the talk, but it will be slightly delayed. And so I'll take hopefully a couple points throughout the talk to answer questions that come in bulk. And if I don't get to your questions at the beginning, we'll take some time towards the end to answer as many questions as you guys have about this. All right, so let's dive straight in. So I always love to start off these talks by telling everyone at least a little bit about how I come at it. So I love massive stars. So don't get me wrong. I also really have a firm affection for our own sun, especially given the whole life on Earth thing. But most of the stars that I study are at least 10 times bigger than our own sun. And I'm interested in studying how they evolve or change with time, and in particular, how they die. So some of the times when I study them, I study the stars themselves. So like looking at fields like this in nearby galaxies, properties of groups of stars to learn about them and how they're influencing everything around them. But some of the rest of the time, I also study something a bit more dynamic. I study explosions. So most of the work that I actually do, and I'm a professor at the University of Toronto in the Department of Astronomy and Astrophysics, is research that generally falls into a field that's known as time domain astronomy. Here is how you should think about it. Much of observational astronomy is essentially static, so operating on timescales that are much, much longer than the human lifetime. So for instance, we don't really get to watch planets form or watch galaxies merge because those processes take millions, if not billions of years to actually occur. However, there are things that happen in the universe on timescales of days to minutes to weeks. And those things include explosions, in particular, catastrophic events that are called supernova. And those are what happen to very massive stars at the ends of their lives. And it turns out that these massive stars and their explosions are very important for almost every area of astrophysics. And I'm not just saying that because I actually study them. And I'm also saying that despite the fact that these very massive stars are incredibly rare. They have really powerful radiation, intense stellar winds. These massive stars are what are making black holes and neutron stars in the universe. And what's most important for this talk, these massive stars and their explosions are actually producing most of the elements in the universe. So I think that Carl Sagan actually said it the best. And he said, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. So this is a beautifully profound and poetic statement, but it's also very nuanced. There are actually many different ways that elements can be formed in the interiors of stars, and some of which actually need explosions. So for the rest of this talk, as I hope you guys are enjoying your latest evening on your couch, the plan for the rest of the talk is to unpack this. How do the stars actually make elements? And importantly, I'm an observational astronomer. I want to try and not just tell you a story and have you assume that I'm correct throughout it. Throughout this, I'm going to try and let you know how we as astronomers actually know. How do we look at data and light that comes from the sky? And how do we actually tell what elements are formed and where? So we're going to try and connect this to astronomical data along the way. So as we said, every element has its origin story. So let's dive in and figure out what they are. First off, though, in order to actually do that, we need to make sure we're all on the same page, as is often the case. So these couple of things I'm highlighting here, nitrogen, calcium, iron, and carbon, those are elements. So let's make sure we're all on the same page. What is an element? Because that's going to be important for where they are actually made in space. So it's long been recognized that there are different materials on Earth that have different properties. Ancient civilizations considered 4 basic elements on Earth. So earth, water, air, and fire. But even from the mid-1600s, well before we had a complete technical understanding of what an element fundamentally was, we had a more technical definition was emerging. It was known that there are certain substances on Earth that are more pure as elements, as it were, that couldn't be broken down into anything that's smaller or simpler, so different constituents. But now, from the 1900s, with the discovery of the electron, the proton, and neutrons, we now have the following understanding of what elements actually are. Some of you may know this, but it's going to be important when we start doing crazy things in the interiors of stars. So what are elements? They are atoms, which are composed of protons plus neutrons, which together form the nucleus of atoms, along with electrons orbiting around them. So the important thing that everyone should remember from their high school chemistry is that what an element is dictated by the number of protons that are in that nucleus, so the number of red ones. So for instance, hydrogen is always going to have 1 proton in its nucleus. Similarly, helium is always going to have 2, and iron is always going to have 26. And so, of course, these different elements can be combined with others to form different compounds and elements. So steel is made of iron along with carbon and other things, but these elements are the fundamental building blocks of chemistry and therefore life. Of course, when we pack them all together, you're going to see this a couple of times throughout this talk, although I really swear this is actually an astronomy talk, not a chemistry one. But when you take all your elements and you stack them up together, ordering them by the number of protons, you get the periodic table. There are about 119 known elements, 90 of which occur naturally on Earth, and others of which have been created in a lab. But where do these all come from? Where do elements actually come from? So to start to answer this question, we actually have to get outside of my wheelhouse, at least a little bit. We have to go back to the beginning of the universe. So what I'm showing you now, this is kind of a schematic of the history of the universe, clearly not to scale. So what we have going on over here on the right, this is present day. This is where we all are now, quarantined on our couches, sitting here on planet Earth. But if we go back a while ago, maybe to 10 billion years ago, life began on Earth. You go back further and further, going to the left, the first stars and galaxies formed maybe a few 100 million years after the Big Bang. But we need to keep going all the way back to start learning about elements. We need to go back to the first 3 minutes after the Big Bang. This is a pretty incredible time in the universe. At this point in time, maybe you should picture the universe looking something vaguely like this. It's this incredibly hot primordial soup of fundamental particles, like really, really hot. It's so hot, we don't even actually have neutrons or protons yet, the particles that we actually even think of as defining the pieces of a different element. So first you're off there at 100th of a second. If we wait to maybe 14 seconds after the Big Bang, the universe will have cooled down a little bit, enough that there are actually physical neutrons and protons now, but no actual elements still. So we need to wait. And again, the universe is expanding and cooling throughout this whole process. Once you get to 14 seconds, now we're at 14 seconds, we still don't have elements, but we have different atomic processes that are taking place, like neutrons converting into protons and back again. And this is going to be important for setting the stage with what elements we actually get. But we really start to get going into things that we see discernible at about 3 minutes after the Big Bang. And at that point, the temperature drops to about 1 billion degrees. So before that, it was even hotter. But we've now cooled down enough to about 1 billion degrees that we finally start to have neutrons and protons start coming together and forming things like hydrogen nuclei. And this is when we really consider that we have elements form in the first place. And this process lasts from about 3 minutes after the Big Bang to maybe 10 minutes after the Big Bang. And after that point, your universe has actually cooled down so much that it's too cool. So elements can't form anymore because now it's too cold. Before 3 minutes, it was too hot, and after 10 minutes, it's too cold. So those 7 minutes were pivotal for the rest of the history of the universe. And what we think is that at that point, after this process happened, called Big Bang nucleosynthesis, about 75% of the matter in the universe should have been made of hydrogen, about 25% helium, and less than 1% lithium, and a few other things. So I told you throughout this that I wasn't just going to tell you stories. So you might be saying, cool, 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 Maria, that's a really great story. But how do we actually know that this is what happened? And this is perhaps the trickiest part of the talk, to tell you how we know for sure that this happened, because it turns out that this point in the age of the universe, 3 to 10 minutes after the Big Bang, is not something that we can actually observe. I'm an observational astronomer, and I cannot point to light that comes to us from that point in the universe. We can't physically observe it. And so how do we know that this is what happened? This is the most indirect thing we have. Basically, we have this theory of, if the universe was this hot primordial soup, which we think it must have been, how would it eventually have cooled down, and what nuclear physics would have taken place to form these elements? But the way we think that we're on the right track is basically, when we look around at the universe, we look around and we see about 75% of everything is hydrogen, about 25% of everything is helium, and you've got a little bit of smattering of other elements that are around. But in general, the observations we do have of what elements are present in the universe match this pretty closely. Almost everything is hydrogen, 75%. So we know that our theory probably can't be too wrong. But it's the hardest to directly observationally observe. Okay, so we're going to come back to this a few points, but that was the first step in the story. So how are we doing on that periodic table that I said we'd come back to? So not great, huh? We've got a couple elements here, and I'm only kind of charitably giving us beryllium as I'm filling this in now, but we have not made very many elements. Now, as I said, like, if you're just thinking total quantity of things in the universe, we're actually pretty good. We've got like 99% of the elements that were ever created in this chart now, but you might notice that there's a couple critical ones that are missing. In particular, most of the types of elements that actually make up you as a human, things like nitrogen, carbon, and oxygen, as well as a bunch of other stuff like iron and calcium that are critical for forming the Earth itself. So if we want to understand where the Earth and where we as humans came from, we need to figure out where those elements came from. So the question is, how do you make new elements? If you have some elements and you want to make some different ones, how do you actually put them together and create new ones? It turns out that this process is pretty darn simple. You just need to take this big red stone that you find somewhere on Earth, and all of a sudden you have as much gold as you want, right? Okay, so this was obviously a joke. Hopefully everyone got the Harry Potter reference with the Philosopher's Stone, but in all actuality, I personally find the early history of alchemy fascinating. Many of the early alchemists were actually the earliest chemists to exist in the world. They helped discover some of the earliest chemical reactions, learned how to produce new materials from others. However, what they didn't know at that point is that their goal of finding the Philosopher's Stone or some other way of turning metals like mercury or into gold, it was fundamentally flawed. And the reason for that was because gold and mercury are pure elements. You can't create them from doing chemical reactions. You actually need to get down into the nuclei of those atoms in order to change one element to the other. And that is an awful lot harder than what they were actually doing. So while ancient alchemy on Earth looked vaguely like this, people in labs with glass beakers, this is what modern day alchemy looks like on Earth. So this is a nuclear power plant. Nuclear power plants are doing alchemy. They are taking certain elements and they are creating other ones. They are putting energy in and getting energy out. And what's most important is that in order to actually create new elements, to get down into the nuclei, to change what something really is, you need very extreme temperatures and pressures that are very difficult to create here on Earth. It's only really in places like nuclear power plants where we do that. So in order to do that in general in the universe, you need to think, where is somewhere that has incredibly high densities and pressures and temperatures that might be capable of actually getting down into the nuclei of atoms? And the answer to that is the interiors of stars. So this happens all the time. Stars are pretty large, they're pretty heavy, and there's a lot of gravity pulling down on them. And it turns out that that gravity pulling down inwards is enough to create intense temperatures and pressures. For example, our own sun, it's something like 5,000 degrees on the surface. But that's kind of nothing on the scale of stars. It turns out down in the core, in the very center of our own sun, it's 27 million degrees. And that's hot enough. And it also has an incredibly high pressure, something like 250 billion times the pressure of the atmosphere pushing down on you now here on Earth. And those temperatures and pressures are high enough that if you take two hydrogen atoms, they will just fuse together and form helium. It's enough that that process just happens. And it turns out in the interiors of stars, you can do that. So the sun is going to be, it is currently fusing hydrogen into helium. When it's done, it will fuse helium into carbon and oxygen. It won't go much farther than that, but submassive stars can actually have enough pressure from gravity pushing down that they can fuse things all the way up to iron just by pushing down and essentially fusing different elements together. So the question is, though, how do we actually know that stars are doing fusion? Again, I just told you that the gravity is enough that this should happen, but how do we as observers actually know that what we think should be happening actually does? So on the one hand, we can make these very detailed models where we take the amount of material that a sun is and put in all the physics we know about and see what happens. And that tells us that fusion should happen in these stars. And those same models are also able to do pretty well at predicting what stars around the universe should look like. So we think that our models are pretty good. However, that's actually not the best thing that we have. The best thing we have is actually pretty close here on Earth, and actually close to me. I'm in Toronto right now. It turns out the best way we know that stars are doing fusion is that through something called neutrinos. So it turns out that those same nuclear reactions that will take lighter elements and fuse them together to make heavier ones, like hydrogen into helium, they don't just take hydrogen and make helium. That process will also release a little particle called a neutrino that will go flying out of the center of the sun and fly out into space, hopefully all the way here to Earth, where they are detected by, for example, the Sudbury Neutrino Observatory, which is located just a few hundred kilometers north of me here in Toronto, where there are different labs that can actually detect neutrinos here on Earth. So we detect tons of neutrinos on Earth all of the time, most of which are coming from the sun. And it turns out that we can measure how many neutrinos we detect coming from the sun, and it matches our theories pretty well for the fact that fusion is actually going on in their core. So that's how we know that stars actually are fusing together heavier elements in their cores. It's little tiny particles known as neutrinos that we can detect here on Earth. All right, so how are we doing now? We're doing a little bit better. We now have created elements all the way up to iron, the periodic table, through fusing things in stars. Now, there's this pesky little fact that a lot of these elements are like stuck in the center of a star. And so if you actually want to make a planet out of it later, or say a human, we're going to need to like figure that out. But let's just say we made it this far. We got all the way to iron by just fusing things in the centers of stars. And we have some pretty important ones. We have all the oxygen, the carbon, the calcium, the iron. We've made most things that make up humans and the Earth. But there are a couple of interesting ones that are still missing. So for example, some people really like gold. That's an important one then, figuring out where did gold come from. We haven't made any of that yet. You might also see things missing like neodymium, which it turns out is very important for making powerful magnets, and it's used in speakers and computer hard drives. I wouldn't be able to be giving you this talk right now if it weren't for neodymium. You're also missing things like uranium, which for all its negative connotations also is probably very important for life here on Earth. There are trace amounts of uranium in the Earth's crust. They actually heat up the Earth and might be partially responsible for plate tectonics and a huge impact then for how life evolved here on Earth. So these are much rarer elements, but they probably are quite important. So it's interesting to consider, where do the heavy elements actually come from in the universe? So how do you actually make heavy elements? Not just light elements, like we were able to get all the way up to iron in the cores of stars, but how do you actually make much heavier elements? So we're about to get a little explosive, but first we're going to take side detour, and we're going to see if you guys get excited about the same things that I do. So fun fact, this is going to come up a little bit. Really hang in there with me, because again, like I said, we're going to get explosive soon. But fun fact, at least to me, it turns out that neutrons can turn into protons. So this process is called beta decay, and it is kind of exactly like what I just told you. So sometimes you can have a neutron, which again, exist in the centers of atoms, but don't define what type of element it is. But every once in a while, a neutron can just spontaneously turn into a proton. And in that process, it's also going to chuck out an electron and a neutrino at the same time. But sometimes this process can just happen. And this, it turns out, is going to be super important for actually creating the very heavy elements on the periodic table. So this is important because, and I'm going to show you a little bit of a video here. What actually happens then is, it turns out, I told you it's really, really hard to get down into the center of like the nucleus of atoms and actually change what the element is. But it turns out it's a little bit easier for a neutron to get in there, because neutrons are neutral. They can sneak in places. So what you have, this is what I'm showing you at this point, is it's a nucleus. Over on the right-hand side, we're going to be counting the number of protons you have, what element you have down at the bottom. So this is iron 56, and the number of neutrons. But how this process is going to work is called neutron capture, followed by beta decay. And we're going to show you movies. Every once in a while, you're going to be in a situation where you've got iron and a neutron just joins. So now you see you have more neutrons. You're still iron because that's how many protons you have. That doesn't change. But now one of those neutrons spontaneously turns into a proton, and you actually now become cobalt. So I'm going to play this again now that you might know. So the idea is you have neutrons that just fly in and manage to sneak in. So that doesn't change what element you are, but you're just sort of adding neutrons throughout the process. And at some point, one of those is going to spontaneously decay and turn itself into a proton, and that's going to tick you up and make you an element that's slightly heavier. So let's watch this one more time. So again, we're still iron. You have a neutron that sneaks in, so your neutrons are going up, but you're still iron throughout this process. All the while you're adding neutrons until one of them, it undergoes this process called beta decay. And now you have one fewer neutron than you had a moment ago, and you've now turned into cobalt. So you managed to sneak yourself up to be an element that's one higher on the periodic table through this process of neutron capture. So it turns out this is going to be super important. So here is just a slightly different way of looking at this. I find this fun. It is a bit of a technical diagram, but it's a fun way of viewing it. So this is a similar process where any point on this chart could be a different element. So we have proton number on going up and down here. So that's just how heavy of an element you are. So like down here, this is where hydrogen would be. And up here, it's more like uranium and other heavy elements. But again, elements going up this way, up and down. And then over here, we're just showing how many neutrons you happen to have in your core as well. So these black lines are roughly where sort of stable nuclei or elements tend to be. So you could have a process where you sort of roughly move your way up. So what happens is if you just sort of grab a neutron, you are going to move over to the right on this plot. And then as that neutron then all of a sudden spontaneously turns into a proton, you're going to move sort of backwards and up. So work your way sort of over and up, over and up, over and up. And you can slowly build heavier and heavier elements by going through this process. So this can either happen slowly, in which case you sort of are going to just sort of trace along this black line, moving slowly up to the right and then up in this diagram. But you could also have a process where if you're in a really extreme situation, you could throw just a ton of neutrons at your nucleus. And that's a process. So slowly going along, we call that the slow process. And whereas if you take instead, and to do the slow process, all you really need to do is capture maybe 1 neutron into your element every like 10 to 100 years or so. So it's a slow process. You just have some nuclei sitting there, and every once in a while, every 10 to 100 years, you grab some neutron and it decays, and you slowly are going to make heavier and heavier elements. Or you could try something else. You could try a situation where you instead throw as many neutrons on all at once, and you're going to do a different process. So what that will look like is this. So watch these colored circles. That's where we're saying we have elements at this point in time. And then all of a sudden, we're going to capture a bunch of neutrons. So we're going to move up to the right in this diagram, and then they're all going to decay back down. So this is going to, I'll show this again. But again, you're watching in this case for a situation where you have a bunch of elements. They're all going to move as far right as possible very quickly, and then decay back down all at once. So that's going to be, you're going to move up. So this is where you're capturing sort of right now, you're capturing a bunch of neutrons. And then at some point, it's going to decay backwards as those neutrons start to turn into protons. So someone did ask, why do neutrons decay into protons? Why do they do that? And why, this came in a bunch of times, why are these protons spontaneously changing? And it turns out that this has to do, there is just a certain probability that that will happen based on the weak nuclear forces, which are actually holding together different protons themselves. So it is just a fundamental process that has a certain probability of happening at any point in time. And so it is very rare, but it happens just enough to be sort of in this balance of important for forming heavy elements. But it has to do with the details of the weak nuclear forces that are going on actually holding things together into what their constituent pieces are. So I just told you a story of, you can either have things, you know, slowly, like we grab a neutron and then it decays and we move up, or we can throw a ton of neutrons on all at once and then they decay back down later. It turns out we actually know that both of these have to occur in the actual universe. How do we know this? We know this because of meteorites. So we can take meteorites that land here on Earth, and you can study very detailed information on what exact elements are there and what exact isotopes. So what elements are there, exactly how much of them there are compared to other things. You can make plots like this, which don't worry too much about the details, but this is just how much of a certain element there is versus how heavy the element is. So heavier elements are over here on the right, and the things that are higher up, there's more of. So like hydrogen is the element that has the most. But you can study from looking at meteorites very detailed patterns of exactly how many of these elements there are and how many of them are compared to each other. And by studying these detailed abundance patterns, as they're called, we know that both of these things have to occur in nature, that sometimes the atoms that exist in the universe have to slowly be capturing neutrons and decaying and making heavier and heavier elements. Or sometimes you have to also have a situation where this happens very rapidly, where you have literally hundreds of neutrons pummeling your atoms per second. And we got some questions, where are these neutrons coming from? We're about to get to that. So let's think a minute though about these two processes. So this is the analogy I want you to think of. So if this slow process of you just have to lazily every 10 to 100 years, one neutron has to wander into the nucleus of an atom and then it eventually decays. there are like random neutrons flying around in the atmospheres of stars. And we think that the physical conditions just in the atmospheres of stars are enough for this process to happen. So this slow process of making heavy elements will just happen in the atmospheres of the stars around you. And again, all that's really needed is every 10 to 100 years, a single neutron finds its way into the center. However, to do this rapid process, which again, we know from meteorites has to actually happen in the universe. Someone first thought of this in a very theoretical way, but we know it has to happen by studying meteorites. In order to make this rapid process happen, you need to have something like 100 neutrons hitting the nucleus of your atom every second. That's mind-blowing. So if this sort of droplet on a pedal is the slow process, how you should think about this rapid process is something like this. And this might even be an understatement. You literally need to have Niagara Falls falling onto a flower in terms of how many neutrons are just pummeling the atom in order to have enough of them capture on such that eventually they can decay down to make these heavy elements. So that's insane. So this is a great question. A number of people are flooding with this question. Where are these neutrons coming from? How do you actually make a situation where you have hundreds of neutrons just flying at your atoms every second? And it turns out, I told you we'd get there eventually, you need something more intense than the interiors of stars. You need explosions. So we are going to talk about explosions that happen in the universe and why we think they can do this process. So if it's going to be explosions, these are some of the most energetic events that happen in the universe. And it turns out we actually need this. They make about half of the heavy elements that exist. We need this process to occur. But what type of explosions are actually doing this? So the first one to consider, one of the most common types of explosions that happens in the universe is a supernova. This is the violent death of a massive star. So a massive star lives out its life. Eventually, it's going to get to the point where it can no longer support itself, and it will collapse inwards and trigger an explosion, like the one that you just saw. These explosions are going to throw outwards several times of the amount of material that's contained in our entire sun, and it's going to throw it out at about the 10th the speed of light. So this is an insanely energetic process. It's energetic enough that it's actually going to take all of those elements that we carefully curated in the center of stars before, and it's going to rip them all to pieces. So I hope you weren't super attached to any in particular iron atom that was formed in the center of a star, because this explosion is going to tear all of them apart. But it's so energetic that that process is going to actually undergo, and it's going to fuse together a bunch of new elements in the process, all from the energy that was thrown out in this explosion itself. So these supernova are incredibly energetic and incredibly bright events. Your typical supernova is going to be 1 trillion times brighter than the sun is. It's going to outshine the rest of the light that's coming from the galaxy it was in for a period of several months. Or my favorite analogy, which was put together by Randall Munroe, who writes the webcomic XKCD, if you had a supernova that went off at the distance of the sun from us, it would be about 1 trillion times brighter than a nuclear bomb pressed against your face. So again, these are really, really bright events. And that's only part of it. It turns out that that light, so again, 1 trillion times brighter than a nuclear bomb on your face, that is only a fraction of the energy that's coming out in these events. You're going to have actually 99% of the energy in this explosion that's going out is going to come out in those tiny particles, neutrinos, that we talked about before. And about 1% of the energy is just going to be in motion. So that process, I told you, you're going to take a couple times more material that's contained in our entire sun and throw it out at a few times or a few percent of the speed of light. That's a lot of just energy in it. So that's about 1%. And if you can do 99 plus 1, there's not enough left. So a very small fraction, so like 0.01% of the energy in a supernova actually comes out in the light that we see. So this is a super energetic process that we think should actually synthesize heavy elements in the process. So only 0.01% of everything is light, but it's my favorite 0.01% because again, I'm an observational astronomer. I take telescopes, I point them at the sky, and I try to observe these things. So what does a supernova look like to me? So it doesn't look exactly like the simulation I just showed you in the background, because most of these are very far away. But what it looks like is something like this. So you've got a galaxy. This is a nice bright spiral galaxy nearby to our own. And this is a supernova that went off in 2011. And this is what it looks like to us. It looks like, if you took any single one of these images, it wouldn't look that much different than the other stars around. But what happens is, over the time period of a few months, it's going to get brighter, and then it's going to fade away. But it looks like a dot. So you should be asking at this point, it's like, oh, wow. I mean, that's beautiful. At least I think it is. But this is beautiful, but it does kind of just look like a dot that's getting brighter and then fainter. So how do you actually know what elements are made in a supernova explosion? And that's a great question. It turns out that there are sort of two key ways that we try to understand what heavy elements you actually create in this insanely energetic process that is a supernova explosion going off. So the two ways that I'm going to let you know. So the first is just that many of the elements that you form in this explosion, when it throws out this material and synthesizes a bunch of other elements, are radioactive. And so it turns out that you can look at a plot like this, and you see that this is what I talked about. The supernova will get brighter, and then it will fade away over a time period of a few months to maybe years. So why we see light over this time period? Because if you think about an explosion here on Earth, you might think of something where it's a flash of light that happens over a period of a few seconds or so. And you should be thinking of that as well. The actual supernova explosion, so the blasting apart of a star, only takes place over a few seconds, maybe. But the material gets thrown out, and then a lot of that material is radioactive. And so after a while, it will decay. And that radioactive decay creates energy that turns into this light that we see. So you can actually trace out how fast the supernova gets fainter over time by looking at different radioactive decay rates. So in this case, is a supernova that formed a lot of radioactive nickel, which decays into cobalt, and then cobalt into iron. And we can actually trace it out by looking at how bright it is and how quickly it fades away. And we know then that some of the elements that were created in this were those radioactive nickel. The second way that we can go through and try and understand what type of elements were formed is by looking at something which is known as the spectrum of the supernova. So what we do there is we take the light from that supernova, so what looked like a tiny little dot on that previous slide, and we break up the light into all the different colors. So what's showing here is blue light on the left and red light on the right. And what you can see here, these are the spectra of a couple different supernovae. So the biggest thing that you should just take away at this point is that there are a lot of bumps and wiggles. And it turns out that these bumps and wiggles we can trace back to individual elements, because there are very specific wavelengths that different elements appear. So for example, in this one on the top, each of these are lines of hydrogen. So we know that a bunch of hydrogen was thrown out in this explosion. And this one on the bottom is slightly different. These are lines of things like silicon and iron and oxygen that we can see, and we can actually trace back to what types of elements are created. So that's super cool. But now what you should be saying is, that's interesting, but looking at what you just said here, you just said things like iron and silicon and hydrogen, which is all great, but it's not actually any higher up on the periodic table than we got to before. And you're actually right. So these supernova are insanely energetic. They rip apart elements and synthesize a bunch of new ones. But in terms of what we actually see, you make it a little bit farther on the periodic table, but not that much. A lot of what you see thrown out in a supernova is actually still around this area, kind of around iron, a little bit further, but a lot of that material is there. And that's true. Almost everything we see in these events is that. And it turns out that even if you look at the theory of it, a vast majority of the amount of elements that are synthesized in supernova and thrown out should be elements that are still roughly around this point. So things maybe up to iron and nickel and cobalt and copper, but not too much further. So that doesn't mean that supernova don't create these heavier elements on the periodic table, all of these things that are still missing, like gold and neodymium and uranium. And in fact, if you actually add up how many of these very heavy elements there are in the universe, you don't need any individual supernovae. You don't need very much of these very heavy elements from any individual supernovae, because these elements are pretty rare and supernovae are pretty common. And so that's great because you don't need very much to be created in them, but that's also tough because if you're forming tons of nickel and only very trace amounts of things like gold and other things like that, you are literally never going to see it in your observations. The signatures are just going to be washed out. And so there's almost no way that we can observationally say for sure that a run-of-the-mill supernova is producing something like gold. So we can't see that. And that doesn't mean they aren't, but it means we need to get at it at other ways. And at the same time, a lot of theoretical models were actually saying that maybe it's actually hard to make a typical supernova do that. And so people are putting together, okay, maybe supernova don't make heavy elements. Where else might you get those insane physical conditions we were talking about? Those like, right, waterfall onto a flower, number of neutrons just pummeling your elements. Where would you get physical conditions like that to make heavy elements if they aren't happening in supernova? And one possibility for that is something called a neutron star merger. So this is going to be the last little bit of our tale, tying things together. So what is a neutron star merger? So a neutron star, first off, is a very dense, dead core of an old star. So a neutron star is actually what is left over after a different star went off as a supernova. So you have a supernova that goes off and you leave behind a neutron star. They are the densest objects that we can have in the universe that aren't black holes. So get any denser and you're going to form a black hole. So it turns out if you manage to make a neutron star and you actually manage to make two of them, sometimes those neutron stars will be close enough together that they will start orbiting around each other and actually eventually merge together. And in that process, they're sort of the gravity is gonna tear them apart, like what you're seeing here, and fling out tons of material, not tons, it's actually a very small amount, but you're gonna fling out some of that material out into the universe when these two things merge together. So we'll show this one more time. If you have two neutron stars that spin around each other, and eventually they're going to distort and fling out some material and throw out. And what's cool is that you might get it from the name neutron star. Neutron star are mostly made of neutrons. So when you take this material and some of it gets flung out, like what you're seeing in this video, that is essentially a waterfall of neutrons. So that is the exact right physical conditions to make these very heavy elements in this rapid process. So we really think that this should happen. It's a much rarer process than a supernova because you eventually, to make this happen, you need to have one supernova go off to make one neutron star, then another supernova go off to make another one. You need those to be close enough together and close enough together that they are going to spin around each other and merge in the age of the universe. So they're rare, so you need them to make more heavy elements each. And also there was this awkward thing in that until a few years ago, though, we had actually never observed a neutron star merger, at least that we knew for sure. So we thought that this should happen. They should make heavy elements, but we had never actually observed them. But it turns out that's just because it is a very rare process and one where the explosion that you expect to see, like how long it will last, should only last for maybe a week or so. So it's very short-lived. So it's hard for us to know where to point our telescopes to see it. So we could use a little bit of help. And where this comes in is something known as gravitational waves. So it turns out there are these detectors on Earth. They are called LIGO and Virgo. But what they are gravitational wave detectors. So they are actually big tunnels in the ground. One of them is in Italy, one is in Louisiana, and one is in the state of Washington. And they are tunnels in the ground that have lasers going back and forth, and they are trying to detect gravitational waves. So gravitational waves, I can answer more questions about that if you have, but eventually it's space jiggling due to very massive objects moving quickly. So in particular, things like two neutron stars spinning around each other very quickly before they merge. Those are the types of things these detectors are trying to find. They've been working on this for decades, trying to detect these signatures of gravitational waves in the universe. And they actually did back in 2015 for the first time. They detected gravitational waves from two black holes, so heavier than neutron stars, but two black holes merging in space. And they got the Nobel Prize for this in 2017. And that's great. That's a little different than what we want, because two black holes merging are going to be black. You're not going to see a lot of light from that. So we were waiting for LIGO and Virgo to detect a neutron star merger and tell us what direction of the sky we should point our telescopes to hopefully see a neutron star merger, to try and understand once and for all whether or not they make heavy elements. So this hadn't happened yet. So LIGO turned on, they found gravitational waves in 2015, and predictions had been that it would take many years until they would find a neutron star merger. But that all changed on August 17th of 2017, when LIGO and Virgo detected a new event. And I'm one of the astronomers who gets text messages and emails whenever they find something. And this is what it looks like on that day. So this is literally the email I got. It's like plain text email that comes in during the day. And the important thing here is they're saying the LIGO scientific collaboration report a new candidate event consistent with a neutron star binary coalescence. So that's a neutron star merger with a false alarm rate of once per 10,000 years. So that just means this is not a false alarm. This shouldn't happen unless it's real. So we knew that this was a real event. This was the first time they had seen it. They were able to tell us this event happened in this patch of the sky that is about 150 full moons across. So we knew that hopefully we were going to be able to find the light from this thing to figure out if this is where heavy elements come from. But we also knew that we were going to have to search for it. And so this is what it looked like. So this is just one way of looking at the sky. It's sort of mapping the entire sky, which is, again, a sphere or a globe, and mapping it onto a globe. So think of this as the entire sky. The most important thing to take away from this is the red area is sort of where on the sky LIGO was able to say this neutron star merger occurred. And the dashed line here is what part of the sky was above the horizon at the beginning of the night in Chile, which is where the telescopes that I used mostly are. And so the important thing to take away is this red area is close to that dashed line. So basically, we knew where this was. We knew we were going to have to search, but it turned out that patch of the sky was only going to be above the horizon before setting for the night for 1 hour at the end of the night. So we knew that we had like 5 hours to prep in order to search. And we're only going to have about 1 hour to search for this new explosion in this sort of large patch of the sky before we'd have to wait an entire 24 hours to look again. But it turns out that this process only took us about 15 minutes. So we started looking with our telescopes and going from galaxy to galaxy, looking for new sources. And I was Skyped into the telescope at the time. And my colleague, Charlie Kilpatrick, was the first one to see this new image of this patch of the sky. So on the left is an old image of this galaxy from the Hubble Space Telescope. And the one on the right is the one we took that night on August 17th. And you see there's this very obvious new source that's there. And it turns out that this was we had to work for a little bit on it, but that was the counterpart to the neutron star merger. So once we found this triggered basically every telescope in the world, and every telescope that's in a satellite orbiting around Earth started pointing at this explosion because we had never seen one of these before, and trying to understand what was happening from this event that had gravitational waves and now light together for the first time. So we sort of went all in with this, hundreds of astronomers and hundreds of physicists working for LIGO. And just a little human interest part of this that I wanted to mention is that this wasn't the only astronomically interesting event that was happening at the same time. So this happened on August 17th. It turns out that August 21st, 2017 was when the total solar eclipse was going across the continental US. So it turns out as astronomers, many of us had plans for what we were going to do for that. So I in particular, along with a few colleagues, had plans to go backpacking across a bunch of national parks in Utah and up to Idaho for the eclipse itself. And so we actually did this. So for about a week after this merger happened, I was road tripping and camping, all the while also coordinating all the observations from Chile for this event. And so this is sort of the trip path of what we did for a week. And this is just what the explosion did over that same time period. So the important thing here is just that this explosion was bright at the beginning, and by about a week later, it was essentially gone. So this was a very short timescale event, and we were coordinating most of the observations from our tent. I actually reduced data, so like analyzed it for the first time in my life in a tent, hopefully the last time, but it was a very interesting experience to go through. But so what does all of this mean? We found light for the first time, but what does it mean for the heavy elements? To show you this, we're going to go back to the two ways I showed you for how do we actually know what kinds of elements are created in supernova. So remember I showed you before that for a supernova, you look at how bright something gets and then how quickly does that brightness fade with time, and sort of trace it to what is the radioactive decay rate for different kinds of elements. So for this supernova, we know that there was a bunch of radioactive nickel and cobalt because of the timescales for how it fades with time. It turns out we could do the same thing for this neutron star merger, but we could map out how it faded over time, over about 20 days, and it matched very closely with theoretical predictions for a mishmash of radioactive elements that are high up in that periodic table. So we know for sure that there were heavy elements that were created and thrown out in this neutron star merger because of the time scale on which it's decaying, which is due to that radioactive decay of all these heavy elements. The other thing we looked at for supernova was by taking their spectra. So again, breaking up the light that we see in that dot into all its different colors and looking for different bumps that are due to different elements. So we do this for supernova. We see things like hydrogen and silicon and iron. We could do the same thing for this event. Now, in this case, we're actually looking at an infrared spectra, but you can see just these broad bumps and wiggles. The black is the data, and the red is a theoretical model for this mishmash of heavy elements high up in the periodic table. So again, we knew for the first time that neutron star mergers really do make some of the heaviest elements in the universe. And we know that from how quickly the light faded away and what the bumps and wiggles in the spectrum actually looked like. So when we piece this all together and actually look at where all these elements come from, we now finally are starting to have this full and complete picture of where all the elements in the periodic table come from. Some of the lightest elements like hydrogen and helium are mostly coming from the Big Bang itself. Things up the middle of the periodic table are formed in the centers of stars and in the explosion of stars and things like supernovae. And then all of these heaviest elements up in the universe are mostly coming from either the envelopes of stars in that slow process, or now we know for sure that a lot of those elements are coming from neutron star mergers. And we only really learned that back in 2017. So there's a lot of stuff to still do, but we finally are starting to tie the bow on having a better understanding of where all of the elements that are in the periodic table and are important for life here on Earth are actually coming from. So I want to thank you all for listening. I know there are a bunch of questions coming in. It was sort of hard to keep up with it while I was going. So I'm now going to go back and look through the chat and hopefully try to answer a bunch of your questions that were coming in as the talk was going on. So feel free to add more questions if you have them now, and I'm going to try and go back and hit a bunch of them. We'll keep chatting for at least 5-10 more minutes. We'll end a little bit after 8, but let me see how many of these questions I can actually get to. So some people were asking, what can we actually do with neutrinos? What is their significance with respect to nucleosynthesis processes? And the big thing there with neutrinos are super important for a bunch of different aspects of astrophysics. You see, they came up a bunch of times throughout this talk. So I think with the neutrinos, there are a lot of people, and a lot of people here in Canada as well, studying neutrinos and what you can learn with them from a physics perspective. An astrophysics perspective, they actually tell you a lot. So in terms of, as I mentioned, they really are the way that we know for sure that fusion is happening in stars because we detect neutrinos from the sun here on Earth. Also, as I mentioned, in supernova explosions, the way our models actually work is that we think that 99% of the energy that is released when a massive star explodes at the end of its life actually is going to come out in neutrinos itself. And so we have detected this once. You have to be pretty close by, and supernova mostly, fortunately, happen pretty far away from us here on Earth. But back in 1987, there was a supernova that went off in the Large Magellanic Cloud, which is very nearby to us. And we actually, at that point, detected neutrinos from that supernova. So that's part of how we know also that our theory for what happens in supernovae is pretty good as well, because we detect the neutrinos here on Earth. You also could learn a lot with them. So it's similar with the fact that, so when you have fusion happening in stars, neutrinos happen from them. So we detect them from the sun, but also at the very late stages, sort of right before a star will eventually explode as a supernova, a massive star, it starts fusing together heavier and heavier elements. And that will create unique signatures in neutrinos. So everyone made a big hubbub about Betelgeuse recently and whether it was going to explode or not. And it will eventually, probably sometime in the next 10,000 years, actually. But if it were going to explode next year, we would have known for sure because we would have detected neutrinos here on Earth. And we hadn't seen those yet. So we knew that it wasn't actually going to explode yet. But neutrinos would be a sure sign of that. OK, let's see. So someone did want to know a little bit more, again, how you explain the part where you figure out what elements are created in supernova by looking at the brightness versus days plot. So that was this one. And so we came back to this one time more, but the real heart of this is the reason that you see light over so much time is that it's not just that all of this energy is created in one burst, right? When the supernova explosion happens. Again, the explosion, like the physical blasting apart of the star, takes place over less than a second. It's really a very quick thing. So you'd see a certain flash of light from that, which we usually do not detect. However, you make all of these heavy radioactive elements, which they decay over time. So radioactive elements have a half-life. And so they take a certain amount of time to sort of undergo radioactive decay. And when they do, that will release energy that then results in light that we see. And so the idea really is it's kind of this stored reservoir of energy. because you make all of these radioactive elements, and some of them will decay right away, but some of them will take longer because there's a certain half-life to how long it takes to decay. And so it sort of dictates sort of how much energy you're going to have at different points in the future based on how many of these radioactive elements you created right off the bat. And this is a very predictable trend of how much energy are you going to produce at a certain time later based on what radioactive element is there. And so we're really looking at these radioactive half-lives from, in this case, it's a single reaction nickel to cobalt or cobalt to iron, versus when we were looking at that neutron star merger, this is a prediction not for an individual element, but for if you have like this super mixture that is full of all those heavy elements on the periodic table. So most of these elements that are heavy on the periodic table here, a ton of them are actually radioactive. And so what we get is this sort of soup of different things decaying at different rates, and you can predict how quickly the supernova should fade away when the light is coming from radioactive decay. Let's see. Do we know if black holes merging create heavy elements at all, or because they don't emit light, we can't study it? That's a great question. So yeah, I talked about how when neutron stars merge, you throw out this material and it has those right physical conditions to make heavy elements. So when black holes merge, there's two sides of this. First, you're right, it's hard for us to study it because two black holes merging, we don't see any light with that because black holes are black. But the other thing in there is black holes are kind of hard to physically conceive of, but unlike neutron stars, the big thing, we talked about a little bit in the Cosmos from the Cows question and answer a few weeks ago, so you should go back to that if you can, but the real difference between a black hole and a neutron star, black holes are a bit denser and heavier, but as a result of that, we stop thinking of them as actually being created of like matter elements. They are literally kind of a hole in space. So they are not, we don't consider them really like made up of atoms or elements or anything like that. Whereas neutron stars still really are made up of matter. And so when you fling them, they get torn apart and can actually create and synthesize new things. So we don't think that black holes merging would create new elements unless they had some maybe material around them that wasn't part of the black hole itself that was somehow involved in that energetic process. Another great question, have we ever observed an exploding white dwarf? Yes, excellent question. So you might see actually that that is one of the things on the chart I'm showing now, which is this sort of summary of where all these heavy elements come from. So we absolutely have observed white dwarfs exploding. So white dwarfs, haven't talked about those yet, but they are the other very dense thing that can be left over after stars die. So you have white dwarfs, then the next densest thing is a neutron star, and then the next densest thing is a black hole. So white dwarfs are what is left over when lighter stars like our sun end their lives. So our sun at the end of its life will become a white dwarf, which is basically this carbon and oxygen ember that's cooling off. So it's very dense, but it's less dense than a neutron star. So only very massive stars make neutron stars, whereas smaller stars like our sun will make white dwarfs. So white dwarfs will not explode if left to their own devices. So our sun will eventually make a white dwarf, and then it will just sort of sit and cool off for, a billion years. And that's all it'll do. But sometimes if you have a white dwarf that it either merges with another white dwarf or maybe sucks some material from another star, you can create a situation where it will explode. We also observe those as supernova. So fun fact, this will be one of the last things I tell you, but so we observe lots of supernovae in the universe, and the supernova that we observe come in two different types. One of them is from massive stars exploding, like what I showed you before, and the other half are from white dwarfs exploding. And it actually turns out, awkwardly, is that the one supernova that I showed you earlier in the talk, so this one, it was the prettiest image I could find, but this one actually is a white dwarf exploding. So I know I was mostly describing the process of a massive star exploding, but this particular supernova, so the one I showed you here, supernova 2011 FE was its name, this is actually due to a white dwarf exploding. And part of the way we actually tell the difference between a massive star exploding and a white dwarf exploding is what elements we actually see in them. So you see slightly different types of elements that come out, and that's due to the slightly different physical conditions that occur when those stars actually explode. So that's a great one. And okay, so last question that we will end on and then finish for this evening. Sorry, I couldn't get to quite everyone's question, was that on that very last chart I showed, there are two elements that are shown in gray. So what's going on there? That's a great question. And so those are two elements, 43 and 61, which we think are not naturally occurring in the universe. So they are ones that are, both of them are very radioactive and unstable, so they don't last long. And we actually don't know of a natural process that creates them. We can make them in labs here on Earth, but it's not clear that they are actually naturally produced in the universe during many of these physical processes that I'm talking about. So they have each been created in labs here on Earth, but they're not really naturally occurring, and each of them are very radioactive, so very unstable, so don't last for very long. But great question. Okay, excellent then. Thanks everyone for asking so many awesome questions, and I hope you enjoyed hearing about explosions in space and where most of the elements come from. And please tune in. We will continue to have more Cosmos from your couch for as long as we're all stuck on our couches. So thanks, everybody.